We're going to go into chapter 5 today, and we're going to first begin by talking about the fundamentals of waves. Compared to chapter 4, okay, chapter 5 and the next chapter, chapter 6, is really a walk in the park. Okay, we have actually covered the two most difficult chapters in Form 4, which is chapter 3, gravitation, and it is difficult because there's a lot of calculation. And chapter 4, heat, because there's not just a lot of calculation, there's also a lot of explanation. And people tend to get confused between the gas laws, lah. Okay, as you all very brilliantly demonstrated last Friday. Okay, we keep getting the wrong gas laws. But compared to heat and gravitation, okay, waves is actually a walk in the park. Okay, I think it is one of the easier topics in Form 4. Okay, although there'll be some parts which will be a little bit challenging. Okay, but in order for us to get a proper understanding of waves, we need to talk about the fundamentals of waves. Okay, so the first thing we need to do is to describe what waves are like. Okay, so if you drop a stone into a water, you will see this ripple effect.
Dropped into the water. What do you see?
You see waves. Okay, so a stone is dropped in the water, and you obviously will see
waves that move outward from the center.
Waves that move outward from the center. Okay, there's always a center where you drop the stone. Okay, and you will see the waves moving outwards. Have you ever stopped to ask now why the waves don't move inward? Why doesn't it, converge into where why is it moving outward? Okay, why is it moving outward? But we find that waves move outward from the center. Okay, and we will look at why as we go along in this chapter. Okay, now besides that, there is also this.
Click on each graphic.
Click on each graphic. Okay, sorry, this is a video, so it's going to click on its own now. So when you shake a string, when you shake a slinky, when you put
you have just observed a few vibrating systems.
Okay, so all these are vibrating
systems produce waves.
Okay, fine. Okay, the first most important thing is any vibrating system, okay, is a system that produces waves. This is the most important thing. Okay, a vibrating system, as the one that you saw over here, okay, when you shake the string up and down, when you move the slinky back and forth, when a ball okay, is hitting the water again and again and again, it is a vibrating system. Okay, satu in Malay it's called system getaran. Okay, so a vibrating system will always produce waves. Okay, when you hit the tuning fork, okay, on the table, okay, it will vibrate. So anything that vibrates, okay, is something that produces waves. And the best example of a vibrating system is your own voice. Okay, you put your hand, okay, on your throat over here and you start talking, or if you don't want to talk, then you go, you will feel, okay, a vibration on your throat. Okay, and you are actually, when you talk, okay, what is happening is your sound box over here, okay, is vibrating. And when it vibrates, it produces sound. And that's why people can hear you talk, although they don't want to hear you talk, but you still, okay, people can still hear you talk. Okay, because of all the vibrations that you are giving out from your throat, your voice box. Okay, so let's talk about this. Study the vibration of a ripple tank. So this is a device that we have in the lab, which we call a ripple tank. Okay, a ripple tank is a tank with water. Sorry, you put water over here, and then there's this one. Okay, so there's this thing over here that is called a dipper. Okay, this thing over here, hold on. Okay, so this thing over here is called a dipper. So a dipper can be like the one that we saw just now. Okay, this is also a dipper, but it is a spherical dipper. Okay, so it just, it creates a kind of waves. But if you have a long dipper like this, okay, it is a long dipper. Okay, one ruler, and then you kasi dip in the ripple tank, and in the ripple tank here there's a lot of water. It's like a pool of water. So the ripple tank, okay, the ripple tank in the lab is a device, or is a lab apparatus that is like showing how, like a lake of water, a puddle of water. Okay, but in a lab setting. So observe the surface of the water when the motor does not vibrate. Okay, the water will be calm. But when the motor vibrates, remember, vibrations produce waves. So the water looks like it's going to move up and down. Not that the water go up and go down, but the water is moving up and moving down. Okay, the same thing you do when you hold a tuning fork. Okay, I don't know if you've ever played with this before, but this is a device. If you're a musician, you will know this lah. Okay, before there were tuners, okay, like the electronic tuners, people used to tune their instruments to a tuning fork. Okay, so the tuning fork, when you hit the tuning fork, pong, and then you put it up to your ear, then you can hear that particular note. So if it is an A, then you pong, like that lah. Okay, so that will be the sound that you will hear from the tuning fork. But can you hear the sound produced by the tuning fork if it does not vibrate? Obviously, there will be no sound lah. Okay, if it's just a tuning fork on its own, it's not going to produce any sound. But when you hit it on a table and it is vibrating, as long as it is vibrating, you will hear the sound. Okay, so again, waves can be produced by an oscillating or vibrating system. So this is a new word. Okay, this is a new word for us, oscillating. Oscillating or vibrating. The word oscillate, the word oscillate is to go back and forth. Pergi ke depan, pergi ke belakang, pergi ke atas, pergi ke bawah, back and forth, back and forth. So this is an oscillation, okay, or a vibration. And we, in physics, we prefer to use the words oscillating when we're talking about waves because it is more accurate. Okay, so a vibrating system or an oscillating system will produce a wave. So in the first situation, the oscillation of a dipper, okay, on the water surface will produce water waves. Obviously lah, kan? So when this goes on, it will produce water waves. But the vibration of a tuning fork, okay, produces sound waves. Okay, so there are different types of waves that we will be looking at in this chapter lah. We look at water waves, we look at sound waves, we look at light waves, water, sound, light. Yeah, I think these are the three most important ones lah. So there's water waves and there's sound waves. Okay, now important thing is this, water waves carry energy too. Okay, now let's observe the effect of energy carried by water waves.
Water waves carry energy too. Observe the effect of energy carried by water waves.
Okay, so this is a famous situation back all the way in, I think, 2000. No, this is in 1990. I can't remember lah. Okay, but the tsunami that hit West Malaysia, okay, at that time, and of course the after effects of the tsunami was that the water waves had this tremendous amount of energy. We don't feel it so much when we go to the beach. Okay, unless the waves are very high, you can actually be pushed by the waves. Okay, to show that waves can actually carry energy and it can transfer the energy over to to whatever thing that it hits lah. Okay, so one of the most important characteristics is that water waves carry energy, and the tsunami shows us exactly that. Okay, so a wave, now we come to the notes. A wave is a process of transferring energy from one location to another, which is produced by oscillating or vibrating system. So a vibrating system produces waves, and the waves transfer energy from one place to another. That is what we call a wave. Okay, previously we were just like, oh, okay, gelombang is just gelombang. Sorry, wave in Malay is gelombang. Okay, not ombak, and definitely not lambayan. Okay, people think that this is a wave. Yeah, actually, technically, this is a wave, and it's vibrating back and forth, like bye. Okay, this is a wave. Okay, this is not a wave. Okay, this is a hand in the air, bye. Okay, bye. Okay, but this is a wave. Wave goodbye. Okay, so waving always implies a back and forth motion. Okay, so a wave is a process of transferring of energy because of a vibrating or an oscillating system. Okay, so
click on the motor to start the vibrator.
Let's click on the motor.
What do you see on the water surface?
What do you see on the water surface? Okay, you find
Water
that.
waves are produced.
Sorry.
What is the direction of propagation
Sorry.
of the water wave? The direction of propagation of the water waves is from right to left. The leaf represents a water particle. How does the water particle move? The water particle moves up and down.
Okay, so this is a pretty interesting thing. We find that the waves, okay, just now we were saying that the waves move from right to left. Okay, when on a water surface, you find that water waves are produced. When you click on a motor, it's going to go up and down, up and down, up and down. It's going to touch the water, and the water waves are produced. But we find that the waves are moving from right to left. Okay, as we saw just now, lah. Okay, the waves are moving right to left. Okay, but when we put a leaf over there, okay, we find that the water particle or the leaf is moving up and down, up and down, up and down. Okay, I want you to highlight this one. The leaf represents a water particle or a water molecule. Okay, and we find that the water particle, it only just goes up and down, up and down. It doesn't go together with the wave. Did you see that in the video just now? Let's show you again. Okay. So take a look at this one. The leaf doesn't move, it just
The water
moves up and
particle
down.
moves up and down.
As the wave is moving from right to left, the water particle or the water molecule or the leaf, fine, okay, is remaining in the same position. It's not going together with the wave. Okay. And this is a very important thing. Okay, so
As the wave passes by, does the leaf move together with the wave? No, the leaf does not move together with the wave. Instead, it moves up and down about its initial position. Waves transfer energy as they move along the water particles. However, the waves do not carry the water particles along with them. That is why the leaf still remains at its initial position. This shows that waves transfer energy without transferring matter.
okay, this is a very important concept which we have to correct in our mind, because we always think that the waves, okay, when the waves move, okay, the water particles, the molecules are moved together with the wave. Actually, it does not. Okay, and we tend to confuse this because we tend to think that, oh, when we swim, or when we are riding a wave, if you've ever gone surfing before, when we're riding the wave, right, okay, the wave is bringing us together along, okay. Actually, it's not. Okay, the leaf does not move together with the wave. Instead, actually, it's just going up and down about its initial position. Okay, that's why the leaf remains in its initial position, because waves transfer the energy without transferring the particle. Okay, without transferring matter. Okay, if this if this is a leaf particle, sorry, a water particle. Okay, if this leaf over here represents a water molecule, you find that the water molecules are actually all remaining in the same place. They are not moving. What is being moved is the energy. Okay, is the energy that is transferred because of the wave vibration. Okay, let's demonstrate this even better with this lah. So when a stone is dropped into a pond, okay, water waves are produced. Very normal. Okay, the water waves propagate on the surface of the water. So the water waves we will see moving this way lah. Okay, very normal lah. You drop a water onto the pond, water will keluar. The direction of propagation of the water waves is from, in this case, is from left to right. Okay, now the cork, okay, this cork over here represents the water particle. Now the cork does not move together with the wave. Instead, it moves up and down about its initial position. Okay, and so this proves to us that what is being transferred by waves is energy. Okay, waves transfer energy, okay, as they okay, as they move along the wave particles. However, the waves do not carry the water particles along with them. Okay, this is something that's a little bit hard initially, okay, at the beginning stages. Something that's a little bit hard for us to grasp because we always think that, oh, okay, if I drop a stone and there's another, there's something else on the other side, that thing is going to be pushed by the wave. Actually, it does not. Okay, you should give it a try. If you have a pool of water at home, okay, you place an object over there, okay, you will find that, as you drop, as the wave propagates, the thing will usually stay still. Okay, the thing will usually stay still. Unless you're moving it, unless you're paddling it or unless something else is pushing it. Okay, but the waves don't actually bring the water particles, okay, along with it. Okay, now let's say we tie a ribbon over here, okay, and then you have this slinky over here lah. Okay, this is so much better if it is done in a lab, but oh well. Okay, so you tie a ribbon over here and then you have two pupils holding this lah. So one person here, and then both of them will listen. Okay, so the first question is, what is felt by pupil at NB, okay, after the slinky spring is moved from side to side? Okay, second question is, what is the direction of the energy transfer along the slinky spring? The third one is, describe the movement of the ribbon. So first question, what is felt by the pupil at NB? Okay, he's going to feel the vibration of the spring. Obviously lah, because he's not moving. A is moving up and down, up and down, up and down. Sorry, left, right, left, right, left, right, left, right. But B is fixed. He is going to feel the energy. He's going to feel the vibration of the spring. What is the direction of the energy transfer? Okay, the energy is transferred from left to right over here. Okay, the energy is transferred this way. But the movement of this ribbon, okay, the ribbon only vibrates up and down, okay, at a fixed position. Okay, so you find that the ribbon doesn't move, The ribbon doesn't move because it is stuck to the slinky over there, obviously. But this is a perfect example for us to show that waves transfer energy without transferring matter. Okay, the single most important thing today, okay, that you need to remember is this. Waves transfer energy, not matter. Okay, it doesn't transfer the water. Okay, don't get me wrong, people. Okay, don't get me wrong. I'm not saying that, let's say you put a boat on the water, the boat is not going to be transferred. It's not. Okay, the boat will be transferred because the energy is pushing the boat out. But the water molecule, okay, the water molecule remains the same. It's just passing the energy to the person next to you. Okay, same lah. If let's say, for example, all of you in the class, let's say you hold hands with one another. Okay, nowadays we're not allowed to hold hands lah. But when you hold hands with one another, one person raise their hand, the next person also has to raise their hand. And if you're holding hands with one another, let's say you're holding hands with one another lah, kind of like this. If one person raise their hands, the other person's hand must also go up, right? You cannot be, I want to go up, but this one don't want. Mana boleh, tidak boleh. Okay, so the water particles, they act the same way. Okay, they are not moving, You are just staying still. You are actually transferring the wave from one molecule to another molecule. Okay, waves transfer energy without transferring matter. The molecule remains there, the same. Okay, it's not moving. Okay, they transfer energy, and that's why people ride the waves, people they swim, you will feel and you will be pushed. Okay, but the water molecules that are pushing you are different molecules at different times. Okay, so the movement of waves from NA to NB transfer the energy from A to B. But the ribbon only vibrates in a fixed position. The ribbon that you see in this picture over here is only going up and down, up and down, up and down. Okay, it's going up and down, up and down. So the ribbon does not move in the direction in which the energy is transferred by the waves. Okay, and so what we can conclude from this is waves are produced when medium vibrates at a fixed position. Propagation of waves transfers energy from one place to another without transferring the matter of the medium. Okay, now the word propagate, okay, dalam bahasa Melayu is merambat. Okay, and it is a word that is very specific to waves. We don't say the waves move. Okay, that's a very like you way of saying it lah. Okay, we say waves propagate. We understand lah. For us, we understand that waves move lah. Waves move from left to right. Okay, but the correct terminology, and I want to insist that you use the correct terminology, is that waves propagate. Okay, propagation of waves, movement of waves, transfers energy from one place to another without transferring the matter. Okay, so perambatan gelombang, okay, merambat dalam bahasa Melayu perambatan lah. Okay, propagation, perambatan gelombang, okay, memindahkan tenaga. Okay, propagation of waves transfers the energy, not the movement. Okay, the movement is, we don't say waves move lah, waves propagate. Okay, so a lot of new words for us here today. Okay, that's why this first subtopic is called the fundamentals of waves, because when we go into the next subtopics, all this you should know. Words like propagate, words like oscillate, words like vibration. Okay, the understanding that waves transfer energy without transferring matter. The thing that I'm repeating again and again, okay, is something that we need to understand. Let's talk a little bit about light waves, sound waves. So sound is a form of energy. Okay?
Sound is a form of wave. Click the hand to beat the drum.
Click the hand.
What happens to the flame? Why?
I wonder whether this is done. Nope, it's not done.
The flame will flicker. Sound waves transfer energy from the vibrating drum to the candle flame, causing the flame to flicker. Click on the start button. As the wave passes through the air, do the air particles move along with the wave? No, the air particles move back and forth or vibrate about their initial positions.
Okay, so sound is a form of energy. What happens to the flame we saw just now? Okay, the flame will start to flicker. Okay, there's nothing that is touching the flame. Actually, you're just drumming on the drum lah. Okay, and there are countless experiments. People have these huge hand drums where they just use air and then people like that lah. Okay, so the flame will start to flicker. So what is happening is that the sound waves are transferring the energy from the vibrating drum, okay, to the candle over here, causing the flame to flicker. Okay, and so because of that, okay, as the wave passes through the air, do the air particles move along with the wave? If you saw the video just now, it doesn't. All the air particles here are just vibrating in their initial position. Okay, they're just going back and forth, back and forth. Take a look now. So they're just going back here and back and forth, back and forth, back and forth. Okay? Okay, back and forth, back and forth, back and forth. And they
air particles.
Okay, and they transfer energy. So the movement of back and forth, okay, also is a transference of energy. Okay, same thing, waves waves transfer energy without transferring the matter. Okay, the molecules don't change place. Okay, so
the orange particle represents an air particle. The air particle transfers energy to the next particle, but stays about its initial position. Thus, as the wave passes through the air, energy is transferred without the transferring of matter.
okay, again, proving the same point. Okay, the air particles transfer energy to the next particle, but it stays in its initial position. Yes, it is moving back and forth, but it is not moving forward all the way. It just transfer energy to the next person. Okay, but it stays in its initial position. So as the wave passes through the air, the energy is transferred, but the matter, this orange particle that you see over here, and all the other particles, they are actually just there. Okay, and their function is just to transfer the energy. They're not supposed to be moving. Okay, and again, the fundamental of wave. Waves transfer energy. I feel like I'm saying this too many times. Waves transfer energy without transferring matter. Okay, the matter stays the same. It's just transferring energy from one person to another. It's not like musical chairs. Okay, so here's another one to investigate the propagation of waves as energy transfer. Let me see. Oh, sorry. Okay, so okay, so the most obvious thing is that you'll find that, as the sound waves move, as the sound waves are produced, the candle is flickering. Okay, if you've ever stood in front of a huge speaker, you would also actually feel the same thing. Not that you will flicker, but you can feel that energy. You can feel that energy from that huge this one, and some people say, oh, it's making my heart beat. Okay, and like whatever, but that's the idea. Okay, you feel the energy, but of course you don't feel the wave coming at you. You don't feel, you don't feel the sound particles hitting your face and slapping your face. Okay, sorry, the question is supposed to come first. Okay, so observe the flame when the speaker produces a sound. The direction of flame seems to move from left to right. Okay, and how does the flame receive the energy to move? Sound waves transfer energy from the speaker to the candle flame. When energy is transferred by a wave from a vibrating source to a distant receiver, there is no transfer of matter between the 2 points. Okay, it's just the transferring of energy. Okay, that's why you see that although there is nothing that is touching the speaker and the candle flame, okay, they are not even touching one another, yet you can see that the candle flame is actually moving. Okay, you see that the candle flame is moving, although they're not touching one another. Okay, so we can only draw one conclusion, is that what is actually moving the candle is the energy from the sound wave. Okay, the energy from the sound wave is the one that is causing the light to flicker. Okay, so energy transfer through sea waves, sea waves motion can be huge. For example, tsunami. Okay, this before, this after. Okay, you can kind of see the devastation. Okay, for example, during the tsunami, the energy carried by the waterways can cause great damage to the surroundings. Most of the energy comes from the winds blowing across the surface of the sea. Okay, that's why if you've ever encountered tsunami, the worst thing you can do is run towards the tsunami. Okay, you kind of want, it's a huge amount of energy, Okay, people, buildings are destroyed. Look at this, just look at the before and after. Before tsunami, wow, nice, thriving town, many houses. After the tsunami, there's nothing left. Okay, yeah, the amount of energy is huge, able to bring down buildings. Apalagi kalau kita, okay, as human beings, stand in front of a tsunami, okay, bye. All right, let's move on to the types of waves. So we find that in order to understand type of wave, we need to understand what is the meaning of the wave profile. Okay, we see a lot of words here. So the wave profile is the shape of the slinky spring as the waves propagate through it. Okay, the shape of the wave is called the wave profile. So in a slinky spring is this. Okay, in a water wave, it's going up and down, going up and down. Okay, now there are two types of waves, which are called the progressive waves and the stationary wave. Okay, now the wave profile propagates with time along the direction of the propagation of the wave. So to us, it looks like the wave is moving. Okay, the wave is moving from this distance, from this place to this place, from this place to this place. So we call it a progressive wave. Okay, the wave is moving. But in a stationary wave, for example, if you pluck a guitar string, you don't see the string moving further and further away from you. Like it's just going there. It's just vibrating back and forth. Okay, so it is another name for stationary wave is a non-propagating wave. Okay, it doesn't move. Okay, the wave is just there. It's vibrating. Okay, it's vibrating. It's producing waves, but it is not moving. Progressive wave is a wave that propagates. It's a wave that moves. Okay, we don't say move, but we say propagate. Okay. Sorry, there are two different classifications of waves. The first one is progressive wave and stationary wave. Under progressive wave, there are two. Okay, but we haven't talked about it yet. Okay, under progressive waves, there are two, but we'll talk about this in a little while. Stationary wave is just none. Okay, and then mechanical waves is another classification. Okay, another categorizing of waves. So mechanical waves are waves that require a medium to transfer energy from one to another. Okay, so examples are water waves, sound waves, seismic waves. Okay, seismic is waves that occur during an earthquake. You know, an earthquake is a vibration. Okay, so it's still a wave. So we call this seismic waves. So these are mechanical waves because they require a medium. Okay. In contrast to that, an electromagnetic wave, okay, is a wave that does not require a medium. Okay, and examples are light waves. For example, the sunlight that comes to us, right? As it travels through space, there is no air in space. There is no air molecules in space. And so light can still come to us, okay, because it does not require a medium to transfer the energy. Mechanical waves like sound, like water, okay, these need, your water molecules are important. Okay, the sound molecules, the air molecules are very important. Okay, because it is the air molecules that is transferring energy. Okay, but electromagnetic waves does not need transfer energy. Okay, so this is another classification, mechanical, electromagnetic. Okay, the first one, as I show you, is progressive and stationary wave. Okay, and under progressive waves, okay, there are two other types of waves, okay, which is transverse and longitudinal. So you might want to make a note at the side over here. Okay, so you have progressive waves, okay, means waves that move. Okay, waves that are moving, not waves that are stationary. Okay, and there are two types of progressive waves. The first one is a transverse wave, and the second one is a longitudinal wave. Longitudinal. No, I think it's longitudinal. Okay, longitudinal. Okay, waves. So understand the categorizations, people. The first one and the main one, okay, is progressive and stationary. Under progressive, there are these two, transverse and longitudinal. We will look at this in a little while. But another type of classification, okay, is mechanical and electromagnetic. And under mechanical is water waves, sound waves, seismic waves. Under electromagnetic is radio waves, light waves, gamma rays. All these are electromagnetic waves. And we will look at electromagnetic waves right at the end, okay, at the end of this chapter. Most of our discussion is going to talk about mechanical waves. Okay, but under progressive waves, okay, there is transverse and there's longitudinal. Okay, so let's take a look at what are transverse and longitudinal waves. Now, if you hold one end of a slinky spring, oh, is this a video? Sorry, hold on, let me show you the video first.
click the start button to get the waves in motion. What is the direction of propagation of the wave? What is the direction of vibration of the spring particle?
Okay, so the wave is the one that you see moving. This blue color dot over here represents the spring particle. Okay, that is represented by this colored thread lah.
The wave propagates to the right, and the spring particles vibrate back and forth. What can you say about the direction of vibration of the particle in relation to the direction of propagation of the wave? The particle moves back and forth, or vibrates, parallel to the direction of propagation of the wave.
Oh, okay. So we find that the blue
dot represents...
Okay, the blue dot represents a particle in the spring. Okay, what is the direction of propagation of the wave? And what is the direction of vibration? We find that the propagation of the wave goes all the way to the right. Okay, this video here shows us this lah. Okay, it propagates all the way to the right. But the spring particle, okay, the molecule is actually moving back and forth. Okay, obviously lah, you don't see the spring changing positions. The spring is just the same position. What is being transferred is the wave. Okay, so we find out that both are parallel to each other. The direction of the propagation is to the right, okay, and the direction of the spring particles is also on the same line. So we call this parallel to one another, and you've learned about parallel and perpendicular in AdMaths, okay, with Kuan Lim lah, okay, I hope. So let's label the parts of compression and rarefaction of the spring and the wavelength of the wave produced. So when the wave is propagating, okay, on a slinky spring, you are going to find these moments where it is loose and where it is tight. You see where this one is loose, where the waves are loose, and where the waves are tight. So where the waves are, the direction of the wave is this way. Okay, the direction of vibration is here. And so where the waves are tight, we call these compression areas. Okay, manakala where the waves are loose, we call this rarefaction. So a lot of new words, okay. Where the waves are tight, we call it compression, and where the waves are loose, we call them rarefaction area. So show the direction of the vibration of the colored thread. The direction of vibration of colored thread is here, back and forth, and the direction of the wave is actually this shouldn't be back and forth. This should just be going forward, I think. Yeah, it should just be going forward because you're pushing it this way, okay. But the movement of the spring, I mean, unless you move your hand back and forth. Oh, it is. Okay, sorry. So the movement of this one is also back and forth. The wave will go forward, backward, until you stop pushing it. But as you move, you're going to see these compression areas and rarefaction areas. Okay. Sorry, hold on. Let me show you the video again, just to show you the compression and rarefaction. Okay. So you see there's this loose and tight, loose and tight, loose and tight, right? Okay, so the loose parts are the rarefactions, and the tight parts over here, okay, the tight part over here is the tight part is the compression, and the loose part over here is the rarefaction. If you have a slinky in your house, this is the best time to start playing with it. Okay, ask your brother, your sister, or somebody in your house, or you tie it to one end, then you just move it. You will see. Okay, you will see these moments, but it's very fast. Okay, if you want to make it slower, take a camera, put it on slow motion, and you can actually see that it's moving fast. That you can see the compression and the rarefaction areas very obviously. Okay, again guys, the words compression and rarefaction are new words. Okay, just like the words longitudinal and transverse. Okay, many new words. Okay, so again, this is why this is the fundamental. So this kind of wave is called a longitudinal wave, okay, where the direction of the spring wave is parallel to the direction of the particle. Okay, the wave that travels along the spring consists of a series of, oh no, it should be compression and rarefaction. Okay, compression and rarefaction. Compressions, okay, and rarefactions. Okay, as shown in this key over here lah. Okay, and I want to introduce to you another terminology, which is wavelength. Wavelength is the distance between two rarefactions or two compressions. So you have one compression here, one compression. This is the wavelength. Okay, let's see. Yeah, okay, sorry, hold on. So this is the wavelength. Or this is a rarefaction, this is another rarefaction. So this length over here is the wavelength. Okay, the distance between two compressions or two rarefactions is called a wavelength, not the distance between the first compression and the next rarefaction. No, nothing to do. Okay, nothing to do with wavelength. Wavelength is compression to compression or rarefaction to rarefaction on a longitudinal wave. Okay, on a longitudinal. So a wave in which the direction of vibration of a particle in the medium is parallel to the direction of propagation of the wave is called a longitudinal wave. Okay, this is the first type of wave under progressive waves. Okay, under progressive waves, is longitudinal. The first type lah. And the biggest thing about the longitudinal is that the vibration of the particle is the same direction or parallel to the direction of the propagation. Okay, now let's look at the other type of wave, which is the not longitudinal. Okay, I think it's called transverse. Oh, hold on. Okay, so you see now that now you see that the thing is going up and down, up and down, up and down. Okay, and you find that the red particle, okay, is moving, is also moving up and down. But the propagation of the wave is to the right. Do you see that? The wave is moving from left to right, but the movement of the particle is going up and down. Okay, so it looks exactly like this lah. The wave is moving this way, but the particle is moving up and down, up and down, up. It's actually not moving at all, Okay, this particle is not moving. Okay, so what is the direction of the propagation of the wave? And what is the direction of the vibration of the spring particle? Okay, the wave propagates to the right and the spring particles vibrate up and down. Okay, and so this is different from the first one that we saw. The first one that we saw, the particle is moving left to right together with the wave. But now it is moving in a different direction. And if you remember your admits, we call this a perpendicular motion. Okay, so the direction of the vibration of the particle and the direction of the propagation of waves is perpendicular to one another. Okay, just now was parallel, now is perpendicular. Okay, now let's label the wavelength. Okay, so the wavelength, okay, sorry, you know what, let me show you this first. So the direction of the vibration of the colored thread is this one, okay, up and down. The direction of the propagation of the wave is this one, from left to right. Okay, and since it is perpendicular, okay, the direction of the spring waves is perpendicular to the direction of the particle. Particle is going up and down, spring waves is going left to right. Okay, and so we call this the transverse wave. So longitudinal, vibration of particle and movement of waves is same direction, parallel to one another. Okay, but transverse wave, the direction of the wave is this way, but the direction of the vibration of the particle is perpendicular to it. So we call this a transverse wave. And the wavelength, the wavelength, if you notice here, is from one down to another down, or one up to another up. I will talk about this up and down later lah. Okay, so this is also a wavelength. Remember just now in the longitudinal waves, we said that the wavelength is the distance between two compressions or two rarefactions. Okay, but in a transverse wave, this stop over here, sorry, I need this video to stop. Okay, anyway, in a transverse wave, the top part over here, we call this a crest, and the bottom over here, we call this a trough. Okay, so for transverse wave, the wavelength is the distance between two troughs, wavelength, or two crests, wavelength. Okay, so the wavelength is the distance between two crests or two troughs, two compressions, two rarefactions in a longitudinal wave. But for transverse wave, it is two crests, two troughs. So the transverse wave looks very different from a longitudinal wave. Okay, and it is different because of whether it is perpendicular, whether the direction of the propagation of wave is perpendicular or parallel to the direction of the vibration of the particle. Okay, let's take a look at this video.
Hi guys, today I just want to show you a demonstration of transverse and longitudinal waves using a slinky. Now, transverse waves, the direction of energy is going to be going forwards, and that's the same with longitudinal waves as well. The energy is going to go this way. But with a transverse wave, the medium, so in our case, the slinky, which is what the wave is going to travel through, is going to be moving perpendicular to the direction of energy transfer. So let me give this a go. So you can see the pulses or the waves are moving from the left to the right. So the energy is moving from the left to the right, but the actual slinky itself is moving perpendicular to the direction. Now another kind of wave is a longitudinal wave. Now with a longitudinal wave, the medium, again which is the slinky, moves in the same direction as the energy transfer. So the energy is moving in this direction. Our wave is going to be, or the medium, the slinky, is also going to be moving in this direction. So this is a longitudinal wave, like sound is also a longitudinal wave. So in this case, you can see that there's a part where the wave gets compressed and a part where the wave gets rarefied, and that these pulses move along in the same direction that the energy is flowing. So that's a longitudinal wave, like that. That's a transverse wave. Okay, bye for now.
Okay, so again, to remind you, the most important thing is that the waves transfer energy without transferring the particle. Okay, you don't see the slinky moving all the way. The slinky is actually stayed still. But what you see moving, is the wave energy. Okay, waves transfer energy without transferring the matter. Waves transfer energy without transferring the slinky. The slinky is still there. It is just transferring the energy from one end to the other end. Okay, so a longitudinal wave, in this case, is a wave, again, in which the vibration of the medium is parallel to the direction of propagation of wave. Okay, transverse wave is perpendicular, to the direction of wave. Two very important, this one. Okay, example of a longitudinal, the most common example is sound wave. Okay, that's why if you notice, the candle moves back and forth. Okay, the sound is going this way. Perpendicular, easily seen, is water wave and electromagnetic waves, which we saw just now. Examples of electromagnetic waves, okay, are light waves, radio waves. Okay, all these are under electromagnetic waves. And all these are transverse wave. Okay, the shape of the wave looks like this. This one, the shape of the wave looks like this. Okay. Okay, fine. The shape of the wave doesn't look like that, but it looks like, the one that we saw in the slinky just now. Okay, so longitudinal, transverse. Okay, fine. Longitudinal is like the ulat bulu, okay, goes back and forth. If you've ever seen a millipede or centipede or, a caterpillar, they kind of move like in a, like a sound waves, longitudinal kind of way. But for a snake, well, snake is more like transverse wave. Okay, so your homework for today is I kind of want you to process everything that I've been talking about for the past 50 minutes, okay? But your homework for today is I want you to, on a piece of paper, I want you to do a comparison, okay? A comparison table, okay, between transverse and longitudinal waves. Okay, so make a comparison table, transverse and longitudinal. Okay, of course, the first one must be similarities lah. Okay, you can do a comparison table or you can do an I-think bubble map if you want lah. But the first one must be the similarities. What is the similarities? And then after that, what is the differences? Okay, so comparison table, transverse and longitudinal waves, state the similarities and state all the differences there are. Include examples as well. Okay, put in a few examples under your differences to complete this one. All right, and hand it in by tomorrow because Friday is our next class. Friday, we will continue with this subtopic. Okay, guys, this first subtopic is very important because number one, it introduces you to a lot of new words. Okay, and number two, it is what it is called. It's called the fundamentals of waves. There are a few things that we need to unlearn. Okay, most of which is that we see as if the waves are moving. Okay, but actually what is happening is that the waves are transferring energy. Okay, that is actually what is happening. Okay, but always we see waves are moving, not entirely very accurate. All right, so please complete this comparison table by Friday, and I will see you all, by tomorrow, because Friday is our next class. Okay.